When I say the word engineer, what pops into your head? Probably someone building a massive bridge, or maybe coding a new app, right? But what if I told you that the most powerful tool any engineer has isn't a wrench or a keyboard, but actually, it's just asking the right question?
Yeah, that's the real puzzle, isn't it? This is the question that sits at the very heart of all great engineering. Before you can even think about building an answer, you have to figure out what the real problem is. You kind of have to become a detective. And today, that's exactly what we're going to do. We're following a group of students as they try to crack a surprisingly tricky case.
So here's the challenge they were given. It seems simple enough. Design a homemade, flameless food heater. You know, like those self-heating meals you can take camping or hiking? Their job was to create their own version from scratch. Easy, right? Just mix some chemicals together and you're good to go. Well, not so fast.
Before they even thought about building anything, the students did something that turned out to be the most important step of all. They went out and talked to potential users, the people who would actually use this thing, the stakeholders. They needed to figure out what people really wanted. And that's where the mystery truly began.
This one question right here gets to the absolute core of it. The stakeholders all said they wanted hot food. But what on earth does that even mean? Is it lukewarm? Is it boiling? Is it so hot it's going to burn your mouth? The students quickly realized their first problem wasn't about chemistry at all. It was about communication. They had to define the word hot.
So, to crack this, their mission became finding what you might call the Goldilocks zone for temperature. You know, not too hot, not too cold, but just right. This was their first big step in turning a really vague goal into a precise, measurable target they could actually aim for.
Okay, so they broke the problem down into 3 really smart questions. First, what's the absolute upper limit? How hot is just too hot for someone to handle safely? Second, what about the bottom limit? Is there a minimum temperature they need to hit for food safety? Like, do they have to cook it? And third, what temperature do people actually like? What tastes best?
So they hit the books, and here's what they found for that first question. Turns out, water at 48 degrees Celsius, which is about 118 Fahrenheit, can cause some pretty serious burns. So, to be safe, the absolute maximum temperature had to be below that. They capped it right there at 47 degrees Celsius. And just like that, one boundary was set.
All right, next question, food safety. And this is where they had a huge realization. Since the food in these kits is already cooked and sealed, it's ready to eat, they didn't actually need to heat it to some super high temperature to kill bacteria. That was a game changer. It meant they could totally forget about aiming for cooking temperatures.
So what about that lower limit, the tastes best temperature? Well, they looked at data from a taste test survey, and it showed something really interesting. While some people were fine with cooler food, the one temperature where every single person in the survey agreed the food was enjoyably warm was 40 degrees Celsius or 104 Fahrenheit.
And boom, there it is. Just like that, they had their first major breakthrough. They finally had a precise, clear, operational range. The target wasn't some vague idea of hot food anymore. It was food heated to a specific window, between 40 and 47 degrees Celsius. The first big piece of the puzzle was officially solved.
Okay, so they've got the temperature nailed down. But as you can probably guess, that's only part of the story. I mean, a heater that works perfectly but is way too expensive or too heavy to carry is still a failed design. In the engineering world, these real-world limits are called constraints, and the students had to figure those out next.
So how do you figure out what's realistic for cost and weight? Simple. You find something that already exists and you use it as a benchmark. So the students got their hands on a commercial store-bought MRE, a meal ready to eat, and they picked it apart to set their own targets. The goal was to make their homemade version even better.
First up, cost. They looked at a bunch of MREs, and the cheapest one they could find was about $12. So to be a better option, their entire meal kit, the food and the heater, had to cost less than that. They set a hard limit of $12 total, and decided only $3 of that could be for the heater itself.
All right, what about weight? They literally just threw the commercial MRE on a scale and it clocked in at around 700 grams. So the team decided their whole homemade kit could not weigh a single gram more than that. And this is a huge deal, because if you're hiking, every single gram counts.
And look at this. This is the result of all that detective work. That huge, messy, vague problem of make a food heater got boiled down to this: 3 beautifully simple criteria. To succeed, their solution had to cost less than $12, weigh less than 700 grams, and heat food to somewhere between 40 and 47 degrees Celsius. Now that is a well-defined problem.
But of course, just because you have a target doesn't mean it's easy to hit, because as every single engineer learns,
pretty quickly you can't have everything. You always have to make choices, and that introduces us to a brand new concept, the trade-off.
So what exactly is a trade-off? Well, it's basically a situation where you can't have your cake and eat it too. Improving one aspect of your design almost always makes another aspect a little bit worse. Think about a car. If you want more horsepower, you're probably going to get worse gas mileage. You can't maximize both at the same time. And these students were about to run into a big one. And here was their central trade-off. Remember that 700-gram weight limit? Well, the more chemical reactants they packed in to create heat, the less room and weight they had for actual food. But on the flip side, if they packed in more food, they might not have enough reactants to get it into that 40 to 47-degree Goldilocks zone. So what do you choose? More heat or more food? You can't have it all.
And this is where everything clicks into place. The students, they thought they were just solving a little problem about hot food, but what they were really discovering, without even knowing it, was a secret process, a powerful, repeatable cycle that you can use to solve any problem. Take a look at this. On the left, you can see their process at the beginning, just a jumble of tasks they had to do, all on sticky notes. But then they started arranging them, trying to find a pattern. And what you see on the right, that's the aha moment. All that chaos suddenly turned into order. They realized the tasks weren't random at all. They fit into a logical pattern, a cycle.
And they realized their own work fit into 3 distinct phases. First, there was define. That's when they figured out the temperature range, the cost, the weight. Then came develop, where they researched different heaters and came up with their own ideas. And finally, optimize. That's where they would test and tweak and improve their design over and over until it hit all the targets.
And the really cool part, the cycle they figured out all on their own, well, it has a name. It's the engineering design cycle, a fundamental process that engineers all over the world use to invent, innovate, and solve some of the planet's biggest problems. Define, develop, optimize. It really is a blueprint for innovation.
And that right there is the big secret. The most valuable thing the students created wasn't a homemade food heater at all. It was their understanding of this powerful process, a process that proves that solving a problem doesn't start with building. It starts with asking questions and defining the problem as clearly as you possibly can.
Look, this process isn't just for engineers building gadgets. You can use it for almost anything. A big project at work, a personal goal you've set for yourself, even a problem in your community. The first step, the most important one, is always the same. Define the problem. So that leaves just one question. What problem will you define next?